Welcome to this explainer. Today we're diving into the hidden science inside our everyday devices, specifically looking at the ultimate engineering solution from microchips. Think about it. When you hold your smartphone, you're literally holding billions of microscopic transistors. They're constantly firing, processing data, and directing electrical currents at absolute lightning speed. But have you ever stopped to wonder what keeps all those billions of signals from just crossing wires and short-circuiting into total chaos? Well, the answer lies in a microscopic layer of armor. Let's uncover the secret force field of modern technology.
We're pulling this fascinating research straight from a masterclass by Dr. Shiv Govind Singh over at the Indian Institute of Technology, Hyderabad. This drops us right into the intense world of advanced cleanroom science. What we're about to explore is the literal foundation of the VLSI industry. Now, VLSI stands for Very Large-Scale Integration. It's basically the incredibly complex process of cramming millions or even billions of MOS transistors onto one single tiny chip. And the research coming out of institutions like IIT Hyderabad gives us this perfect, unfiltered look into exactly how these chips are forged.
So this brings us to a pretty massive mystery. Why exactly did silicon become the undisputed king of the modern tech world? I mean, we call the global epicenter of technology Silicon Valley for a reason, right? But if we look at it chemically, there are actually other elements on the periodic table that theoretically could do a way better job at transmitting signals. So why in the world did the entire global electronics industry place a multi-trillion-dollar bet on this one specific element?
To answer that, we really have to look at its competitors. Elements like germanium and gallium arsenide, they actually move electrons much faster. Germanium has incredible electron and hole mobility, which theoretically means a faster chip. And gallium arsenide boasts this direct band gap that is absolutely fantastic for optoelectronics. But they lack one absolutely crucial thing that silicon naturally has, and that's the ability to form a stable oxide. See, when exposed to oxygen, germanium might oxidize, sure, but it's volatile. It literally just washes away in water. And gallium arsenide, it simply doesn't form a cohesive protective oxide layer at all. Silicon, however, is uniquely capable of wearing its own rust as a perfect, impenetrable shield.
The absolute heart of this superiority lies in a transformation process called thermal oxidation. This is where raw silicon undergoes a literal trial by fire to grow its protective armor, silicon dioxide. In the absolute simplest chemical terms, it's just Si plus O2 becomes SiO₂. But in practice, this isn't just, painting a coat of primer over a surface. The oxygen actually reacts with the silicon wafer, consuming the top layer of the silicon to grow this oxide. It's an integration of the material itself. Because it literally consumes the silicon beneath it, it forms this incredibly smooth, nearly perfect atomic interface between the raw silicon and the new silicon dioxide layer.
This transformation builds a virtually indestructible force field with a whole set of chemical superpowers. First up is physical and chemical passivation. Basically, this prevents environmental contamination from completely ruining the highly delicate circuitry underneath. It is incredibly stable, holding its integrity down to a vacuum of 10 to the negative 9th torr, and it easily shrugs off temperatures past 900 degrees Celsius. On top of that, it acts as a phenomenal chemical diffusion barrier. When engineers try to dope the silicon with elements like boron, phosphorus, or arsenic to tweak its electrical properties, the silicon dioxide blocks them completely. That's what allows for ultra-precise circuit drawing. Plus, it has a massive 8-electron-volt band gap, making it a near-perfect electrical insulator.
But the absolute ultimate superpower of this device, dielectric, is its jaw-dropping breakdown field. We're talking 10 to 15 million volts per centimeter. Just take a second to really conceptualize that. To break through this microscopic barrier, you would need the equivalent of a lightning bolt's electrical pressure scaled down to the atomic level. No way, right? This means you can pack millions of transistors tightly together side by side on a chip, and this ultra-thin layer of silicon dioxide will consistently prevent the electricity from jumping between them. It is quite literally the perfect, unwavering traffic cop for billions of fast-moving electrons.
Now, we can basically separate this protective tech into two main categories: thermally grown oxides versus externally deposited oxides. Thermally grown oxides are exactly what they sound like. They're grown natively out of the silicon itself through intense heat. This includes your native oxide, gate oxide, masking oxide, and field oxide. And because they grow directly from the substrate, that atomic interface we talked about, it's virtually flawless. On the flip side, deposited oxides are essentially sprayed or laid down on top of the silicon. They don't consume the silicon, but they also don't have that same perfect atomic level bond that you get from the thermal growth process. Both definitely have their uses, but thermal growth, that is the gold standard for absolute precision.
Okay, so to actually grow this armor, we have to transition from chemistry equations on a whiteboard into the highly controlled forge of a modern suited-up cleanroom. If you step inside a facility like NanoX at IIT Hyderabad, you'll immediately notice the yellow lighting everywhere. That is specifically to prevent UV light from unintentionally exposing sensitive photoresists used in other steps of the manufacturing. And check out those specialized protective suits. They aren't just there to protect the scientist from chemicals. They're heavily designed to protect the silicon from the scientist. Seriously, a single flake of human skin, a stray eyelash, or even just a tiny speck of dust could completely short out a microscopic circuit, turning a multi-million-dollar manufacturing process into very expensive trash.
As you might guess, the equipment required for this involves some massive, intensely precise machinery. The main tools of the trade include horizontal and vertical tube furnaces, rapid thermal processing units, and specialized atmospheric and high-pressure oxidation systems. Back in the early days of chip building, horizontal tube furnaces were the standard, basically just long, glowing, heated tubes. But modern fabrication, it often relies on vertical tubes. It saves a ton of floor space and greatly improves the heat uniformity across those silicon wafers. Alternatively, rapid thermal processing uses arrays of incredibly high-intensity lamps to flash heat the wafers in a matter of seconds, rather than slowly baking them for hours on end.
Let's trace how this actually flows, starting from the gas and water inputs over at the bubbler vessel, straight into the quartz tube where the heated wafer racks sit directly in the oxidation fire. So, the bubbler vessel keeps highly purified water at about 95 degrees Celsius. Oxygen or inert gases pass through this, picking up water vapor, and then they travel directly into the quartz tube. Inside that tube, red-hot resistance heating coils are baking the silicon wafers sitting on their quartz carriers. And why quartz? Well, quartz can withstand immense thermal shock in extremely high temperatures without melting or outgassing any contaminants. So it operates as the perfect, entirely sterile crucible for growing our silicon dioxide armor.
Inside those red-hot quartz tubes, engineers manipulate the environment using three distinct methods. We've got dry oxidation, wet oxidation, or pyrogenic oxidation. Dry oxidation uses pure oxygen gas. It's a pretty slow process, but it creates a highly dense, incredibly high-quality oxide layer that is just perfect for delicate gate oxides. Wet oxidation, on the other hand, uses the water vapor from that bubbler vessel. It's much faster because the hydrogen and oxygen molecules diffuse through the silicon more rapidly, which makes it great for thicker, structural masking layers. Finally, pyrogenic oxidation actually combusts hydrogen and oxygen directly inside the tube to create an ultra-pure steam, giving you a great combination of speed and high purity. Manufacturers really have to carefully balance these methods, choosing slow perfection for the delicate brain of the chip and faster methods for the bulkier structural layers.
As we continue to push the absolute limits of technology, it leaves us with a pretty provocative thought. How will this highly engineered rust need to adapt when our microchips become near atomic in size? I mean, we are currently designing transistors that are literally only a few atoms wide. At that quantum scale, even a chemically perfect layer of silicon dioxide starts to experience quantum tunneling, where electrons simply teleport right through the barrier as if it wasn't even there. While we are definitely exploring new exotic materials to solve this next great hurdle, the legacy of thermal oxidation, the process of forcing silicon through a trial by fire to build its own armor, remains the fundamental bedrock of the digital age. So the next time you tap a screen, remember the atomic fire that made it all possible. Thanks for joining me on this explainer, keep wondering, and I'll see you in the next one.